Number 35, page 107. It's a second order non-homogeneous linear differential equation. To solve for this, first we need to solve for its homogeneous part. So y double prime plus y is equals to 0. Its characteristic equation is m squared plus 1 equals to 0, and its roots is to plus minus I. And then its complementary solution is c1 cosine x plus c2 sine x. And then by method of variation of parameters, we need to solve for yp. So we need to get the Wronskian of y1 and y2. Cosine x, this is negative sine x, and this is sine x, cosine x. So the Wronskian is equals to cosine squared x plus sine squared x, which is equals to 1. Then solve for u1 prime, which is equals to 0, then 1 plus sine x then cosine x over 1 is equals to sine x, negative sine x over 1 plus sine x. So our u1 is equals to the antiderivative of negative sine x over 1 plus sine x. By integration of rational functions, we will arrive to an antiderivative which is negative x minus 1 over tangent x over 2 plus 1. Next, we need to solve for u2 prime, which is equals to cosine x, negative sine x, 0, 1 over 1 plus sine x all over 1. So it is equals to cosine over 1 plus sine x for u2 prime. So u2 is equals to the antiderivative of cosine over 1 plus sine x, which is equals to the ln of 1 plus sine x. So our yp is equals to negative x minus 1 over tangent x over 2 plus 1 cosine x plus sine x ln x. No, sine x ln of 1 plus sine x. So the complete solution is equals to c1 cosine x plus c2 sine x minus x cosine x minus cosine x over tangent x over 2 plus 1 plus sine x ln of 1 plus sine x. Problem number 3, page 111. X squared y double prime minus x y prime plus y is equals to x to the fifth. This is an example of a Euler-Cauchy differential equation of a second degree. So its characteristic equation is am times m minus 1 plus bm plus c equals to 0, where a is equals to 1, b is equals to negative 1, and c is equals to 1. Substituting the values, so we get m minus 1 minus m plus 1 is equals to 0. So it will be equals to m squared minus 2m plus 1 is equals to 0, which is just equal to m minus 1 squared equals to 0. So the roots is 1. So we have 2 equal roots. So I think it's case 2. So it's the complementary solution yc is equals to c1 x to the x to the m x plus c2 x to the m is 1 ln of x. To get yp, we can use the undetermined coefficient method. So let's assume that yp is equals to ax to the fifth. Then we take the first derivative of yp, which is yp prime is equals to 5ax to the fourth, and yp double prime is equals to 20ax cubed. Substituting the values of yp prime and yp double prime to the original equation, so we have x squared y double prime, so it's 20ax to the fifth minus 5ax to the fifth plus ax to the fifth, which is equals to x to the fifth. So equating the coefficient, we can have 20a minus 5a plus a is equals to 1. So our a is equals to 1 over 16. Then our yp is equals to ax to the fifth, so 1 over 16 x to the fifth. So our complete solution is y is equals to c1x plus c2x ln x plus our yp, which is 1 over 16 x to the fifth. Number 2, page 121. This is a problem about a spring mass system with a given W equals to 15 grams, K is equals to 3 grams per centimeter, and Y is equals to negative 1 cm, and VO equals to 7 cm per second. Its differential equation for a simple harmonic motion is mass times d squared y over dt plus ky is equals to 0, where mass is equals to weight divided by gravity plus ky equals to 0, and we can divide divide the whole equation with g over w, so it will be a second order linear differential equation in its standard form. So kg over wy. At this point we can get its characteristic equation, and its we can get its roots. So this is m squared plus kgwm equals to 0, where k is equals to 3 times the gravity is 9, given gravity is 980 centimeters per second squared, over the weight is 15, m equals to 0. Then we will have a value of 3 times 980 divide 15, 196. There's no m. M squared plus 196 equals to 0. So m is plus minus 14i. So this is case 3, unreal roots. So our y is equals to there's no e to the 0, 1, so c1 cosine 14t plus c2 sine 14t. At time t is equals to 0, y is equals to -1. So y 0, so c1 cosine 0 plus c2 sine 0, this is equals to -1. This one cosine of 0, 1, so c1 is equals 0. So our c1 is equals to -1, and we will input c1, so it will be y equals to negative cosine 14t plus c2 sine 14t. Then at time is equals to 0, velocity is equals to, our initial velocity is 7 centimeters per second. So to get we know that velocity is equals to dy over dt, so we take the derivative of y with respect to t in order to have the initial velocity. So dy over dt is equals to sine 14t plus 14 c2 cosine 14t, which is at t equals to 0, v is equals to 7. So it will be 7 is equals to 14 sine 0 plus 14 C2 cosine 0. This is equals to 0, so it will be 1/2 C2 cosine 0 is 1, so our C2 is 1/2. So our y will be equals to negative cosine 14t plus 1/2 sine 14t.